Hi, everybody, and welcome to part 3 of our notes. We are going to be switching up a little bit and still talking about reactions, but now talking about something that is known as chemical equilibrium. All right. So once a reaction begins, really two things can happen. The first thing is that it can go to completion. And by that, we mean the reactants are going to become the products, and that's all you have. And that certainly happens when you, let's say, burn a piece of paper or something like that. That's the situation. The second thing that can happen, and is very common, is what is known as reaching chemical equilibrium. So let's just kind of walk through an example and see what I mean by chemical equilibrium. Here's an example of the decomposition of dinitrogen tetraoxide, N2O4, which is a clear colorless gas. And it breaks up into nitrogen dioxide, NO2, which is actually a brown colored gas. All right. If this reaction were to go to completion, you would expect to see in the container that this is going on, it to go from completely colorless clear to brown. Instead, you get kind of this in-between yellow color, and it stays that color. So let's see why. All right. So at first, all you're going to have is what we call the forward reaction. You're just going to have this reactant turning into product. But then after a while, all right, once some of this product is formed, some of it actually starts turning back. So we still have the forward reaction going, if you notice my arrow from left to right. But now we're going to get a little bit of what we call the reverse reaction. And sorry, the font's so small here. The reverse reaction. And the reverse reaction is where your products are going back to reactant. Eventually, you end up reaching chemical equilibrium. And we show that in one of two ways. We either have an arrow drawn like that, or you may see two arrows of equal size going back and forth, showing the forward and the reverse reaction are at equilibrium. Now, let's talk about what chemical equilibrium means, because that word equal really kind of messes with us sometimes. What it means, and this is really important, okay, so put a big star here. It means that the forward and the reverse reactions are going at the same rate. Again, going at the same rate. It doesn't necessarily mean that you have the same amount of reactant and product. All right, that is totally dependent on the reaction, and we're going to look more deeply into that. But the forward and the reverse reactions are going at the same rate. That is what chemical equilibrium means. All right, so to give us an idea as to how much reactant or product we have once this equilibrium is reached, we talk about what's known as an equilibrium constant. All right, an equilibrium constant, and this gets the abbreviation capital K, little eq. All right, it is the ratio of the product concentration to the reactant concentration. All right, so here's just kind of my generic reaction, okay? I'm just going to show you how to set up a KEQ, all right? And then we'll work more into doing the calculations. So KEQ, always on the top are your products, and it is about the concentration of those products. So here we go. On the top, concentration of C. When we put something in brackets, remember, brackets stand for concentration in molarity. And we're going to use that a lot in this unit, use that a lot today. So the concentration of C to the power of C. And what I mean by that is whatever that coefficient, these lowercase letters stand for the coefficient, okay, from that balanced equation, times the concentration of D to whatever that coefficient is, A to the A, B to the B. All right. Now, let's take a look at what this value, once we calculate it, is going to tell us. If your KEQ value, all right, is greater than 1, if the numerator is higher than the denominator, that means at equilibrium, you have more product. So then at equilibrium, you have All right, more product. If KEQ is less than 1, that in equilibrium, you have more reactant. Because again, think about mathematically, that means that your denominator, which are your reactants, is greater than your numerator. If you get a situation where your KEQ actually equals 1, that's the only time when you have the same, okay, amount of reactant and product. And product. All right, so KEQ is a value that lets us know, all right, how the equilibrium is affecting our amounts. So if my job is to produce a certain product, I want to choose a reaction that has a KEQ that's much greater than 1, all right, or as high as I can possibly get it, because I want as much product before this reaction. Basically, it's not stopping, but it's not going to give you any more. So that's what our KEQ is going to tell us. So now have your calculators out because you are going to need them. And we're going to go through the different types of KEQ problems. Okay, so here we go. For equilibrium problems, and we have several of them. All right, type 1 is calculate KEQ when you know the concentrations at equilibrium. Well, this is the easiest one by far. All right, and we're going to first, as always, set up your KEQ expression. So KEQ is going to equal, I'm looking at my balanced equation, concentration of C to the power of 1. We don't usually write those ones in. Times the concentration of D squared. Why did I have the squared? Because it has a coefficient of 2 in front of it. Over the concentration of A squared, again, coefficient, times the concentration of B. That's the first thing you always want to do. Get in the habit of writing the KEQ expression without the numbers, then you can always put in the numbers. So now here we go. At equilibrium, A is 3, B is 1, C is 4, and D is 0.5. So that means for C, I just said it was 4, so it's going to be 4 times 0.5 squared over 3 squared times 1. All right, and take a moment. You're going to put that into your calculator, and you're going to get 1.5 times 4 divided by 3 times 3. And you should get KEQ is equal to 0.11. And for something like this, give me 2 to 3 significant figures. That's great. There is no label, all right? We just always write KEQ is equal to. And again, this is giving us an idea as to what is going on at equilibrium. So pretty straightforward, all right? The second type of problem is finding a missing concentration, all right? So at equilibrium, okay, we have that A is 2.5, B is 3. What is the concentration of C? I've given you your balanced equation right here. I've also told you what the KEQ is. All right, so let's set this up always. Remember, write your expression based on your balanced equation. So C squared over the concentration of A times the concentration of B squared. Okay, well now we know that KEQ is 16, all right. We don't know what C is, so I'm just gonna make C my X, or you can leave it at C, it doesn't make any difference. All right, over, but we do know what the other ones are. So 2.5 times 3 squared. Okay, take a moment, and you should find that you get C squared, if you will, or X squared, if you wanted to do it that way, 360, okay? Then your concentration of C would therefore, because you have to take the square root, is going to be 19, all right? Great, so we have 19. Now, in this case, we do have a label, and that label is capital M because you are solving for concentration. All right, for the same reaction, if C is equal to 5 and A is 1.2, what is B at equilibrium? So pause the video and give this one a go as well. All right, so again, we're using this same KEQ expression right here. So I know that 16 is going to be equal to 5 squared over 1.2 times my B squared. So that gives me B squared is 1.3. Concentration of B is going to be 1.1 molar. All right, we always like to circle our answers and be nice to our teachers about that. Okay, great. Final one takes a little bit more work. All right, and is actually really our most practical and the one that if you move on in chemistry, you'll really be using the most. And that is determining equilibrium concentrations from initial concentrations. So this is where we know what we're starting with, which makes sense. We're the ones starting the reaction, so we're going to know how much we start with. But we don't necessarily know how much, what those concentrations are going to be once equilibrium is reached. And these are called ICE problems. All right, and you're going to see why in a second. So let's take a look at the question. For the reaction, A plus C yields D plus B. The initial concentration of A and C are 2 molar, and the KEQ is 3.3. What are the equilibrium what are the equilibrium concentrations for all species? Well, the first thing I'm going to do, and I'm going to do it up here just so I don't run out of room, I'm going to write my KEQ expression like I always would. So that's going to be concentration of D times the concentration of B over the concentration of A times the concentration of C. Great. I am now going to set up what is known as an ICE chart. So I want you to set this up just like I am doing. I am going to take my equation and I'm going to write it just like this. So concentration of A, concentration of C, just notice I'm just taking them straight down. Concentration of D and concentration of B. All right. I am now going to write the letters I, C, E, ICE. I stands for initial, for your initial concentration. C stands for change, what's going to happen to it. Okay. E stands for equilibrium. Okay. That's where we're getting the ICE chart from. So I, C, and E. Take a moment to write this in. All right. So the initial concentrations, these are all concentrations. Remember, I have these in brackets. So the initial concentration of A and C are both 2. So the initial concentration of A is 2. The initial concentration of C is 2. Well, what about the initial concentration of D and B? Well, D and B are our products. So initial means before the reaction even starts. So I don't have any products before the reaction starts. So that's going to be 0. All right. The next step is change. Well, what's going to happen? Well, as this reaction goes, you're going to lose some A and some C, right? It just makes sense. You're going to make some product and you need to know, sorry, this should have had a double arrow up here because this is obviously a reaction that's at equilibrium. And so you're going to lose some of this product, this reactant. It's going to turn into product. Well, how much? Well, we don't know how much, so we're going to call that X. But what we do know, because A and C have the exact same coefficient in front of them, all right, that it's going to lose the same amount. And we're just going to call that X. So the change is minus X, okay? If A had a coefficient of 2 in front of it, that would be minus 2X, all right? But it doesn't. It has a 1. So these are minus X. Well, what about D and B? How are they going to change? Well, they're going to gain whatever A and C lose. So plus X plus X. Again, we're basing this on the balanced equation. So had this had a 2 in front of it, it would have been plus 2X. But we're going to keep the math nice and simple, okay? Then what happens at equilibrium? Well, at equilibrium, you are just going to combine these two. So it's going to be 2 minus X, 2 minus X, 0 plus X, which is just simply X, 0 plus X, which is just X. I am now going to put these into my KEQ expression. All right. I told you what the value of KEQ was. All right. So I know that 3.3 is going to equal the concentration of D. Well, D is X. times the concentration of B. B is X. So that's going to be X squared over the concentration of A times the concentration of C. 2 minus X times 2 minus X. So that's 2 minus X squared. All right. Now, don't worry about the math getting any more complicated than this. I am going to make sure that they're perfect squares so it works out really nicely for you. If you are to go on in chemistry, all right, then certainly you would be using the quadratic equation and all sorts of things like that so we could make the numbers a little bit more fun. But we're going to make this nice and straightforward. So all you do is you take the square root of each side. All right, and once you do that, you're going to find that you get 1.82, and just use your calculator for that, is equal to X over 2 minus X. All right, then you're going to go on ahead and solve for X. You will find that X equals, 1.3. Now, if you have a hard time solving for X here, please come and see me and we can talk you through how to do that, all right? So you're gonna solve for X, you're gonna find that X is 1.3, okay? And now you're gonna have to go back and answer the question. So the initial concentrations of A and C, what are the equilibrium concentrations? So here we go. Okay, well, X is 1.3, so the concentration of D, which is the same as the concentration of B, that is 1.3 molar, because we know that they are X at equilibrium. Concentration of A, which is the same as the concentration of C, right? All right, so A and C are the same. Well, they're 2 minus X. So 2 minus 1.3 is going to give you about 7. We'll put a 0 there just so we don't have one significant figure. And those are your final answers. All right. We're going to get plenty of practice here with our ice problems. All right. So hope you are enjoying our chemical equilibrium and have a great day.